So in this video we're going to be looking at the chain rule. So the chain rule helps us with composite functions. So if we have, if we have a function in which we have, say, x, and that g of x is our function that we have. Composite functions let us combine functions, so we can say f of g of x. So our composite function h of x is equal to f of g of x. We can say that this is our composite function. So that would be, well, you can note it as like such: f times g. That is a composite function, which basically means this right here. So, given two functions, f and g, the composite function, which can be written like that, is actually f times g of x is equal to f of g of x. That is a composite function. So, we're going to look at the derivative of this function. So, let's just say we have a function let's say we have our function h of x is equal to our composite function. That means our derivative of this is going to be h prime of x is equal to f prime of g of x times g prime of x. So this is the chain rule, because basically, I don't know why they called it the chain rule. I'm guessing because you gotta like bring this one along with the next link in the chain, but I didn't name them. So let's just try an example. Let's say we have h of x is equal to x squared plus x to the power of 3 over 2. So let's say the way we interpret this is that our g of x is equal to x squared plus x, and our f of x is going to be x to the power of 3 over 2. So when you have f of g of x, basically g of x is this inner function here, which we put into here. That'll give us that. So by our definition of our derivative, we can do this. The derivative of our inner function is going to be 2x plus 1, and then of this one is going to be 3 over 2x 1 over 2. So now we can actually plug in our f prime of x, well, x squared plus x is equal derivative of that saves a lot of time just by looking at it. So let's do another one. We can do, let's try y equals u cubed minus 2u plus 1, but u is equal to 2 root x. So we're going to find the derivative dy over dx, but we also want to find it when x is equal to 4. We want to solve for that. So if we apply our inner function, this is our inner function, that is our outer function. So our outer function derivative is going to be 3u squared minus minus 2. And then our outer functions will be, let me just put this in bigger ones, 2 times, and then we have the square root. So square root is always, to the power of half, so 1 over 2x to the power of negative 1 over 2. So we have or I guess the 1 over 2 and 2 will cancel, so I'm just left with 1 over root x, and then I wanted to find it at 4, so x is equal to 4 and u is equal to 2 root x. So if we plug that in, if u equals if you plug 4 into that, the square root of 4 is 2, 2 times 2 is 4, so u is equal to 4. And 1 over root 4 is 2. So I'm left with 4 squared is 16. 16 times 3 is, 4 times 4 is 16 times 3. 48. 48 minus 2 is 46 times 46 over 2. I'm left with 23. And there we have it. Let's do one more. Let's do x, but instead of x I want to put g of x, so x squared minus 5 to the power of 6 times the derivative of the inside, which is 2x. So the 2 will multiply times 2x times 7, so 14x times x squared minus 5 to the power of 6. And that's how simple it really is. So if you want to actually try this on your own, you can try this one. Let's see something. Say we have h of x is equal to 2x squared plus 3x minus 5 to the power of 4. Find h prime of x. And throw your answer in the comment section below. But that's all for this video, and I'll see you in the next one. Okay, so in this video we're going to be looking at velocity and acceleration. The reason why we're going to be looking at this right in the middle of our derivatives section is because derivatives are actually how we can calculate rates of change, and velocity and acceleration are indeed rates of change. So let's say you have a function that describes the distance. If you take its derivative, you're going to find the rate of change at which the displacement or the distance is being traveled. You'll have the velocity. And if you take the derivative of velocity at any given point as it's changing, that will give you the acceleration. And that is why we look at velocity and acceleration, because if you do the first derivative and the second derivative, that's how you get to these. So speaking of first and second derivatives, let's actually just try an example. Let's say we have f of x equal to x over 1 plus x. I want to take the second derivative and I want to solve for x equals 1. So what I'm going to do, I could use the quotient rule, but I'm going to quickly use the product rule. And it's just quicker for me to do. So I should have the derivative of the first one, which is 1 times plus the derivative plus x actually times the derivative of that one, so that'll give me negative 1. Derivative of the inside. So I have 1 over x plus 1 x will be cancelled out, so I'm just left with f prime of x equal to 1 over x plus 1 squared. So now I want to take the double derivative of that. Let me just rewrite this like that. X plus 1. So I'm going to do the derivative of that using the chain function. So that'll leave me with the negative 2 in the numerator, and then the x plus 1 to the power of 3 in the denominator. So now that I have the second derivative, I can actually plug in 1. So that will leave me with 2 to the power of 3, which is negative 2 over 8. And there you go, which is actually negative 1 over 4. And that's that. So, what does that actually mean though, if we were to look at this? Like, that was just me taking a second derivative. Let's actually put some context into this. So let's say we have a function which is s of t equals 6t squared minus t cubed, and t is also greater than 0. So t is time and s is in meters. So what we want to do is find, well, this s being in meters, this is a function that describes the displacement. So now I want to find the velocity and acceleration at t equals 2. It's very simple. S prime of t is equal to 12t minus 3t squared. And if we plug in 2 into that, 12 times 2 is 3 times 2 squared. That should give me 12. It's 24 minus 12. So 12. And if we do the second derivative, which will give me velocity, I should get 12 minus 16. So if I plug in 2 into this, I should get 0, which will tell me that if this is the function for displacement at 2 seconds, at the second, oh, that's interesting to say, at 2 seconds, the velocity will be 12. Meters per second, and then here it'll be 0 meters per second squared. So let's see what else we can do here with this. this world problem, we can ask ourselves, questions like, let's see, what can you do with this? You can figure out at what time is the object at rest. So when an object is at rest, it means it's not moving, which means when our s prime is equal to 0, so 12t minus 3t squared so you can actually just factor this out. So 3t should give me 4 minus t. 0 equals, so at t equals 0 and at t equals 4. So at these 2 points, the object is at rest. You can also figure out in which direction it's moving at t equals 5. And that's easy to do. You can just look at the velocity again. So if you plug in 5 into there, 12 times 5 minus 3, 5 squared, that should give you negative 15. So when you see a negative 15 velocity, that just tells you that it's moving in the negative direction. And you'll learn more about that in the vector section of calculus. So what else can we do? Actually, I think I'll stop this one here. I think we covered the key points, that this velocity and acceleration, and you'll see that here we had an acceleration of 0. That's okay. That's not wrong. If something is moving at constant velocity, that means the acceleration is 0. It's not getting faster or slower. So that is correct. So what else do we have? Maybe I could leave you with something to try on your own. Say y equals x squared plus 1 over x squared. Find the second derivative and throw that into the comments. But for now, that's all for this video, and I'll see you in the next one. Okay, so in this video we're going to tackle optimization. So one thing that I want to quickly go over, the max and the min of any function. Say you have a function or whatever, it's modeled by f of x. We know that f prime of x at any given point, say here, is like the equation to the tangent line. So with that being said, when you have something that is here at the exact max, the tangent line will actually be equal to 0. Same for a min. It will be 0. Remember that. That is because the rate of change at that point, when you do the line, the tangent line, that will be just a straight line. So with minus 2x, right? So the area for this is going to be the area of this function is going to be x, which is one side, times 800 minus 2x, which is also 800x minus 2x squared. So remember what I said in the beginning. Sorry. The derivative of this will give us when this will give us the maximum of this function. So if we do the derivative, it'll be 800 minus 4x. And if we set this equal to 0, and solve, we should get 4x equals 800, x equals 200. So, what does that tell us? At 200, we're going to get 200 times 800 minus 400. That's just this one, minus 2x. So that should give me 80k meters squared. And there you have it. So x will be 200, and then here you'd have 400. That will give you the maximum possible area, the dimensions. So we can actually try a different one now. Let's do, this might be harder to draw. Let's say I have let's say I have this sheet that is 60 centimeters on one side and 30 centimeters on another side, and I want to make this sheet into a box. I want to fold it upwards. But I want to fold the edges by a certain amount of the same amount on every side. X on each side. But I want it in a way that will give me the largest volume possible when I fold this into a box. So I know that my box's height when I fold it will be X. My length will be 60. Let me write this somewhere else. Will be X. Length will be 60 minus what I'm going to lose here and here, 2x 360 minus 2x, 30 minus 2x. And if we expand this, we can get 4x cubed minus 180x squared plus 1800x. And I guess you already know what we're going to do with this. We're going to get the max and the min, well in this case the max, so IV prime of x is going to be 12x squared minus 360x plus 1800. I can actually factor out a 12. So, if we set this equal to 0, the 12 will divide by both sides, and I'm just left with this x squared minus 30x plus 150. So I'm going to put this, I need to find these zeros for this. So if you remember in our old formula, we're going to use our quadratic formula, negative b plus or minus yeah, that should be it. So I should end up with x b squared, so 900 minus 4 times 1, so 4 times 150. That should give me 600. 900 minus 600. That should give me 300 over 2 times a, which is 2. So I'm left with x equals 15 plus or minus 5√3. So let's see, x will be about 23.7 or x will be 6.3. So I'm gonna go with this one because that one clearly is not feasible in our situation, because if you plug it into here, you're going to be in the negative length, so cannot be that, so it has to be 6.3. So if you actually plug in back into our v of x formula, so let's put 6.3 back into you should get 5196. Okay, so in this video we're going to be tackling exponential derivatives or derivatives of the exponential function. So, if you remember y equals e to the power of x, there's not much to this. So, if you have y equals e to the x, the derivative of that is going to be e to the x. I'm not making that up, that is something you can look up. So, let's actually just start doing some examples here. So say if I had y equals e to the 3x. In our last video we did derivatives of composite functions where we used the chain rule, in which this would be our internal function. I'll put an I there, and that would be our external function, where you would have f of x being I guess e would be that, or something to the power of f of x would be something to the power of, let's say, y to the power of 3x, and then g of x would be our logarithm. So, that, ignore this, I'm not 100% sure about that, but if you were to use the chain rule here, you would do e to the 3x times the derivative of our external function, which is going to be 3. So our derivative is going to be 3e to the 3x, because, let me see if I can get this right, if f of x equals e to the g of x, and my g of x is going to be 3x. Yeah, that's how it's supposed to be. So f prime of x, which is that, is going to be f of x times hold on. Yeah, f prime times g prime of x, which is basically e to the g of, when it comes to, logarithms. Sorry, exponential functions, you have e to the g of x times g prime of x. That's what I was trying to get at. So, you can even do that with, say, e to the power of x squared minus x. Now you know how to do it. You just rewrite it and then multiply it by the derivative of the exponent, which is going to be 2x minus 1. Let's see what else we can do. Say we have f of x equal to x squared e to the x. We can use the product rule here. So we can put times e to the x plus x squared times the derivative of e to the x, which is also e to the x. So now we can just simplify e to the x factored out to x plus x squared. Simple as that. Let's try another one. F of x equals 3e to the x squared. Let's try to find f at -1, or f prime at -1. So, let's start by taking the derivative first. We can set the 3 aside and just do the derivative of e to the power of x squared. So we know that that's going to be x squared times 2x. So we should get 6x e to the x squared. And if you plug in a -1, you should get -6e. Because -1 squared will become +1 e to the 1 is just e. And that'll become -6. So what else can we do? Let's see. While we're on the topic of exponents, I guess I could show you f of x equals b to the power of x. Let's see. If you have an exponent like this, then your derivative is going to be the ln of b times b to the power of x. So that's pretty straightforward, right? So if you have f of x is equal to 5 to the power of x, your f prime of x is going to be ln 5 times 5 to the power of x. Same with if you have f of x is equal to 5 to the power of 3x minus 2. You're going to have let's see if we can use the, no, I guess not. I'm wondering if we can use the chain rule here. Because the f prime of x should give me, let's see, what do we have? 5. I know I have my ln 5 for sure. And then let's see if I can use the chain rule here, where I have f of x is equal to 5 to the power of g of x, and g of x is equal to the exponent there, 3x minus 2. So if I use the chain rule, prime of x is going to be 3, and the derivative of that is going to be ln 5. So I should have, I can write it down here. F prime of x is going to be the original times ln 5 times the derivative of the exponent, which is 3. And there you go. I guess that, this rule only holds true if it's just an x. If you have b to the power of g to the x, then your derivative will be f prime of x equal to the original function g of x times the ln of b times g prime of x. And I guess that made sense earlier when it was just b of x, because you would have b of x times ln b, and then the derivative would just be 1 anyways if it was an x.